Hello, my name is Xunyu Wang. My individual project is about deep learning asset pricing. There are three parts: models, results, and conclusion. The history of asset pricing can be traced back as far as the late 18th century. One of the most famous models is the three-factor model created by Fama and French. Market, risk, and size value are the main three factors in this model. The model has been shown to explain the variations in the returns of diversified portfolios well. However, it is not suitable for a single stock, and the assumption of this traditional model is very strict. For example, it assumes that there are no security transaction costs. It is not practical in real life. As technology advances, deep learning models are being applied to asset pricing. They do not need strict assumptions, and it has been proved in some research that the deep learning models are better than the traditional three-factor model. One of the most classic deep learning model is feed-forward neural network. It is called FNN. There are three kinds of layers: input, hidden, and the output layer. In my task, the input layers is 55 firm-specific characteristic of a single stock in month T. The output layer is the expected return of this stock in month T plus 1. I will explain later why I choose these 55 firm-specific characteristic as the input. Hidden layer has 8 layers in my task. The size of the layer is 256, 128, 64, 32, 16, 8, 4, and 2. The function of the FNN is hard to explain. It is the black box problem in deep learning. The real data will be processed through every layer. The weight matrix and bias vector will be trained automatically at each layer. Finally, the output can be got. When I applied the FNN, I found it took a lot of time to train the model. I think that maybe the inputs are too many, so I applied autoencoder to compress the data. Extracting the factors by autoencoder is a good way to reduce dimensionality. The original data is fed into the first layer of the encoder. It was processed in the hidden layer. Finally, low-dimensional data is the output in the coder area. It is very useful to keep the important information and shorten the training time. Finally, I introduced the long short-term memory network. It is called LSTM. LSTM has 3 gates to forget what is not important in previous data and use the important information to predict the price or return in the future. The structure of the 3 gates is shown on the picture on the right. The LSTM are designed to capture long-term dependency. There are 2 important hyperparameters in LSTM: lookback and the number of the in-purchase. The number of the in-purchase is how many times you want the LSTM to train. Lookback is actually a value. For example, if I set the lookback at 30, the LSTM will use the data in the last 30 period to make a prediction. I would like to predict the future value of this stock. Finally, I want to know what affected the price or the return. I choose 55 firm-specific characteristics such as asset turnover, inventory turnover, receivable to current asset. The reason I chose them is that they change more frequently, unlike microeconomy indicators such as federal interest rates, which change several times a year. I think these firm-specific characteristics may have great impact on the price. I did a linear regression on the characteristic and the expected return on the next period. In the left picture, we can see the result is very bad. The blue points barely fall on the gray endpoint, which means the predicted value is far away from the actual value. The R-squared can also prove that. It is minus 1.28, which means it is worse than using the mean value as the forecast. The R-squared is the metric used to evaluate whether the model is good or not. I think there are 2 reasons. The first is that the relationship is nonlinear, and the second is that the characteristics do not influence the return. So I use the FNN to explore if the relationship is nonlinear, or I tried the FNN with the different hidden layers, and I found the Model 3 is the best. It has 8 hidden layers. We can see from the right picture that the R-squared of the Model 3 is about 0.2 for both training and test set. It can also prove that the relationship between the characteristic and the return is nonlinear. Unlike linear regression, the FNN does not allow direct assessment of each variable's impact on the outcome by looking at the magnitude of each variable's coefficient. This is the black box problem in deep learning, so I set one variable as 0 each time to see how the performance will be worse. I use difference between the original R-squared and the R-squared without this variable as the metric. Finally, I found the characteristic which is important to the prediction. NPM is the most important. NPM is net profit margin. Next step, I use the autoencoder to extract the factor. I want to extract the important information and shorten the training time. It can be seen that the R-squared is negative when the D factors were set to 32, 16, and 8. The main reason is that all the information in the 55 firm-specific characteristic is important to Model 3. Extracting D factors leads to loss of information. It makes the nonlinear relationship between the return and the characteristic not significant. Now I know the characteristics do influence the price or the return. I pick 20 stocks randomly and use FNN to predict their return, then get the return of the portfolio. Next, I use the three-factor models to do a prediction on this profit, on this portfolio. I divided the stock in this portfolio into 6 groups. Then I get the SMB and HML, which are two important factors in three-factor model. From the picture on the right, we can see that the FNN is better than three-factor models. The green line represents FNN model, and the blue points represent the actual value. I think the result is not good enough, so I introduced the LSTM. When I was choosing the best hyperparameters, I found when I set the input as previous price instead of the 55 characteristic, the result is better. So I changed my input as previous value. Next, I test the performance with different inputs and look back. From the picture on the right, we can see that many lines are close to the actual value. Considering R-squared and mean-squared error, I choose the number of the input is 70. I set the lookback as 10 because when the lookback is 10, the R-squared is the closest to 1 and the MAC is small. After choosing the proper hypermeters, I used the LSTM to make the prediction for 20 stocks and get the return for the portfolio. From the picture, we can see that the prediction made by LSTM is the closest to the actual value. However, the R-squared is still negative. I think maybe the hyperparameter of the LSTM is only suitable for one stock. Maybe I need to set different hyperparameters for the other 19 stocks. The conclusion is that I proved the weak nonlinear relationship between the expected return and the 55 firm-specific characteristic, and I found which characteristics are important. I extract the factors by autoencoders, and I found the deep learning model is better than traditional three-factor models in predicting the return of the portfolio. Finally, I found that the LSTM model has very good performance in predicting the return of a single stock. Thank you.